All right. Okay. So about gradient boosting. So I think this is part kind of 11 from my data science video project. So here we go. So we will learn how to build and optimize models with gradient boosting. So it's one of the algorithms called gradient boosting. This method dominates many kaggle competitions and achieve state-of-the-art results on a variety of dataset. For much of the course, you have made prediction with random forest method, which achieve better performance than a single decision tree, simply by averaging the predictions of many decision trees. So that's what basically random forest is. Basically, instead of just one kind of decision tree, you have multiple, um, and then you average it. Okay. So revert to the random forest method as an ensemble method. So it's a ensemble means you kind of mix and match. You kind of you know build build it from like a Lego block. You build on top of one another, right? So by definition, ensemble methods combine the prediction of several model, which means several trees in the case of random forest. Next, we learn about another ensemble method called gradient boosting, right? So gradient boosting is a method that goes, I'm just gonna put this a bit high up, through cycles to iteratively add models into an ensemble. It begins by initializing the ensemble with a single model, whose prediction can be pretty naive, even if its predictions are wildly inaccurate. Subsequent addition to the ensemble will address those errors. Then we start the cycle. First, we use the current ensemble to generate predictions for each observation in the dataset. To make a prediction, we add the prediction from all models in the ensemble. So we add the predictions from all models, okay? These predictions are used to calculate a loss function, like mean square error, for instance. So that's called a loss function. It's a new term. Ooh, so scary. But basically, how big is the error is, right? It's because once you create a mathematical function, once you train an algorithm, in this case, it's called gradient boosting, right? So you got all of the hyperparameters kind of fill in, right? The A, B, C parameters, whatever. And then you want to use that to predict, right? So you put the test data set, and then you get the prediction. And then you want to compare that prediction from the test data set. Um, no, it's not, sorry. This is we're still talking about the training and the validation. So you use validation, and then you use the result of that prediction that you compute using the validation data set, and then you compare it with the output from the validation, right? And then you can see how big is the error, right? So that's all. So the testing is just for the submission purpose. Um, so we use the loss function to fit a new model, then that will be added to the ensemble. Oh, so you use that loss function to fit a new model. How does this work? So you have the error. How big is the error or the loss function? Okay. Specifically, we determine model parameters so that adding this new model to the ensemble will reduce the loss. Oh, okay, okay. I see what it means. So side note, the gradient in gradient boosting refers to the fact that we'll use gradient descent on the loss function to determine the parameters in this new model. Okay, so because you know like how big is the error, so you use that kind of like a benchmark because you're gonna introduce a new model to the ensemble, and then you recompute the whole thing and recompute the um the error. So this is kind of like deep learning basically. Huh, interesting. And then you want to know you have to know that the error has to be smaller and smaller. If it's bigger, then you kind of like probably throw away that model kind of, or use a different parameters, or you use grid search to choose different parameters in such a way that your error is kind of like lower than the previous one, or you can use the what do you call that? The other one, yeah, some kind of grid search, but it's more like a very specific parameters. Like the earlier session we used random forest, but we only um, kind of play around with the number of trees, the n estimator. Remember the with 50, 100, 150, 200, 250, 300, and then we kind of loop, and then we choose the lowest number of mean square absolute error. So you can use that one too. Uh, but the more sophisticated one, you can use grid search CV for that. Oh, so this reminds me of deep learning. But anyway, those of you who are not familiar with deep learning, this is interesting. Don't worry about it. You're learning. You can go to my other YouTube channel that's talks about what is deep learning, what is the proof why deep learning works. But it's this is interesting. It's kind of like a meeting in between machine learning and deep learning. It's like the introduction. So this is where kind of you kind of learn about the basic of deep learning through this gradient boosting as XGBoost, because you kind of like add a model. First, you test one model, you compute the error, and then you introduce a new model, and you compute the error. You want the error to be lower and lower and lower and lower. So this is the same as deep learning. The difference in deep learning is the model is just one big giant model instead of one small chunks model. That's the difference because it's a giant mathematical functions. But after that, it's kind of the same because after that you fine tune the hyperparameters using a gradient descent. Okay, cool. So finally, we add the new model to assemble and repeat. Okay, so we have first naive model here, right? And then we use it to we train it, and then we use it to make predictions. We calculate the loss, and then we get a new model to train it, um, and then we add that new model to the ensemble, and then we use it to make predictions. The thing I'm not sure is, do you average it out or you use kind of the best model? Anyway, so we begin by loading the training and validation data in xtrain, xvalid, ytrain, and yvalid. Okay. In this example, you work with XGBoost library. XGBoost stands for Extreme uh, Gradient Boosting, which is an implementation of gradient boosting with several additional features focused on performance and speed. Scikit-learn has another version of gradient boosting, but XGBoost has some technical advantages. Okay. In the next code, we import the Scikit-learn API for XGBoost. So XGBoost XGB regressor. This allows us to build and fit a model just as we would in scikit-learn. As you will see in the output, the XGB regressor class has many tunable parameters. You learn about those soon. Okay, so you kind of import the XGB regressor from XGBoost, and then you put it create a placeholder for it. My model equals to XGB regressor, and then you just fit it. This is where you train. Okay. And then you also make prediction and evaluate the model. So you again import the matrix for that with algorithm, which is mean absolute error, and then you use the validation data to predict um, the model that you already trained, and then you put it inside the prediction placeholder, and then over here you just print it out. So and then you get mean absolute error 276, and then you do after that you do parameter tuning. Has a few parameters that can dramatically affect accuracy and training speed. The first parameter you should understand are an estimator. Um, so this is number of how many times. Oh, it's different. Okay, I thought it's number of trees. The one in random forest is now is the number of trees, right? But this is the number of how many times to go through the modeling cycle described above. It is equal to the number of models that we include. Oh, okay. So it's kind of the same. Yeah, okay. Because in a random forest, number of estimator is the number of trees that you want to use, right? This one is the number of models because it's using different models. What kind of model? I don't know, to be honest. Um, could be yeah one decision tree, could be I don't know, could be even random forest, could be I don't know if you use support factor machine or just linear regression. I'm not sure. So so if it's too low, then the result it will cause underfitting, which leads to an accurate prediction on both training and test data. And if it's too high, okay, so it's too high means the number of engineers is too high. Cal is overfitting, okay, because it's kind of more complicated, the mathematical function, because you just put in a lot of um, algorithm, which is algorithm is basically a mathematical function, right? A different kind of mathematical function. The more you put, the more complicated it is. And then the more complicated it is, there is a probability, high chance that your algorithm, after you train it, it become overfit. Overfit means it's only good on the training. That means you get a really high accuracy on the training or low error score on the training. But when you test it or when you deploy it in the real world, when you submit it for prediction, it gives like a high error. So I need to break on here.